Okay, so the delta G zero determines spontaneity of reactions, whether the reaction is going to occur. K determines how far the reaction goes towards the products. A larger K, you're going to have a more negative delta G naught, favoring the product. Smaller K, more positive delta G naught, reactants favored. So there's a relationship between the reaction, between the equilibrium constant and the free energy change. So we've got the relationship we were just working with, where delta G is equal to the standard delta G plus RT natural log of Q. At equilibrium, we know that K is equal to Q, and delta G for the reaction is equal to 0 at equilibrium. So delta G for the reaction is 0. Delta G standard plus RT natural log of K. So that's a relationship. It's not necessarily very useful. We can put one on one side and one on the other side. I think your book does it this way. Delta G 0 is equal to negative RT natural log of K. So there's a relationship between the standard free energy change and the equilibrium constant. The larger that K is, the more negative delta G is. And if K is small, delta G becomes more positive. Any questions? So here looking at an equilibrium between two gases, gas A and gas B. If K is small, less than 1, at standard conditions, where the pressure of A is equal to the pressure of B, they're both 1 atmosphere, Q would be equal to 1, and we would see that the reaction would go in the reverse direction. Here, where K is larger than 1, under standard conditions, still Q is equal to 1, and the forward reaction is spontaneous, because Q is going to K. So whatever direction will cause Q to become closer to K is the direction that's going to happen. At equilibrium, under standard conditions, if K is equal to 1, it will come to equilibrium at standard conditions. Any questions? So we can predict which direction the reaction is going to go. Okay, calculate standard free energy change at 298 for this reaction. We know what the equilibrium constant is. So we're going to use that relationship we just looked at. Delta G reaction is negative RT natural log of K. Oops. After this chapter, you're probably going to remember 8.314. Temperature's 298 Kelvin times the natural log of K, which is 81.9. So then delta G is going to be negative 109.14 joules per mole, usually expressed in kilojoules, and so it's negative 10.9 kilojoules per mole. Under standard conditions, is the forward reaction spontaneous? Yes. Kp tells us that the products are favored as well. Any questions? You guys are very quiet today. Not necessarily a bad thing. So we see that free energy change depends on the equilibrium constant, and the free energy change also depends on temperature. So we can figure out what the temperature dependence of the equilibrium constant is. So what if we set these two equations equal? Because this is delta G standard and this is delta G standard. So let's see what we can come up with here. Negative RT natural log of K is going to equal to delta H minus T, delta S. Okay, so let's divide by negative RT to get rid of this. So I'm going to get natural log of K is equal to negative delta H for the reaction over R times 1 over T minus, here we've got and this is over negative RT. So this T is going to cancel that T. So those T's cancel. And we've got a negative down here and a negative up there. So that makes this positive. So the natural log of K is equal to negative heat of reaction under standard conditions over R times 1 over T plus the standard entropy change divided by R. This is in the form of a line, y equals mx plus b. So we can graph natural log of K versus 1 over the temperature. The slope will equal negative delta H over R, and the intercept is equal to delta S over R. So much neater. There we have it. This is the straight line form. Yes?
Why do you have to separate the R and the T in the denominator of the delta H, by delta H?
The reason I separated the R and the T here is because I want to use this as my X variable, 1 over T. And so I'm pulling that out so that I can see clearly that this is M and this is X. So this is what I'm graphing, 1 over the temperature. And this is going to be the slope of the line. So if we graph natural log of K versus the inverse of the temperature, we get a straight line.
I see. So the 1 over T would be the horizontal axis?
Yes, 1 over T is the x-axis, the x variable. And it's it's very common to mess around with equations like this and rearrange them and try to get them into the form of a line. Because if we have the line, then we can graph it. And we can find things like you can experimentally determine the intercept, and knowing R, you can calculate delta S, whereas that's not something that you might be able to measure directly. So this is going to be useful over a limited temperature range. You can use this to find the standard heat of reaction and the standard entropy change of the reaction by measuring how the equilibrium constant changes as a function of temperature. Temperature is obviously relatively easy to measure. The equilibrium constant, how could we figure out what that is? You'd measure one of the products or reactants, right? If you know the concentrations and you have some control over that, then you can calculate K from your measurements, and so this is a way that you can get delta H and delta S. We can also make a two-point form of this equation, and this should look, this type of an equation should look familiar from Chem 1A. Like, yeah, I vaguely remember something like that. So the natural log of the ratio of the equilibrium constants is equal to negative delta H over R times 1 over T1 minus 1 over T1. T2 minus T1. You know what I mean. It's up there. Oy. We did an equation very similar to this with pressures, with partial pressures, vapor pressures of gases. So we can find delta H for the reaction by measuring the equilibrium constant at two different temperatures, and we can find K2. We could also find K2 knowing delta H and K1. So if you wanted to know, well, what's the equilibrium constant at this other temperature, you can use this two-point form of the equation to find that. Any questions?